Hello, and welcome to today's problem, lowest common ancestor of a binary search tree. Let me just readjust my camera so I'm a little bit more downward. Okay, there we go. So, given a binary search tree, we're going to want to find the lowest common ancestor of two given nodes in a BST. And that's defined as two nodes, P and Q, and the lowest node that has both P and Q as descendants. So in this case, where P is 2 and Q is 8, the descendant is 6, and where P is 2 and Q is 4, the output is 2 because a node can be a descendant of itself. Okay, that makes sense. Okay, so interesting. Okay, well, one thing we know is that the property, it's a binary search tree. So everything on the right side is greater, everything on the left side is less than. We can somehow probably use this property in order to solve the problem. Question is, let's have a look. Okay. One thing we can do is lowest common ancestor. Okay. What we can do is for a given value, we can figure out whether or not that's the root one by checking to see whether or not like the left and the right are children of it. So yeah, that's the first step we need to figure out. We need to have something as a result. And okay, we'll start off with having the let's see, like currents have that equal to the root, and then returning the cur at the end. Now, while the next thing you need to do is loop through for every single value, and you want to keep checking to see what the current value is. So let's think about how we could do this. We have 628. In order to check that it's a lowest common ancestor, we have to arrive at P and Q at some point. So we have to check if P dot val if okay. So okay, since we know it's a binary search tree, we know like if the current dot value is if P dot val is less than the current val, then we know that we're going to want to go to the left of the tree. Left of the tree, I think. So we have the current value, P dot val is less. We go to the left because definition of a binary search tree is all the values to the left of it are less than. And we keep on basically iterating through that, so on and so forth, until we find that value. Likewise, it also has to be the same thing if it traverses to the right. Like if the value is greater, then we have to keep traversing rightwards until we find that value. Yeah. So yeah. Let's write that up first. We have while select true for now. If the p dot val is less than the cur dot val, then you want the okay. Actually, let me think about this. Okay, so my thinking right now, if p dot val is less than the current value and q dot val is greater than the current value, then Oh, wait a minute. No, sorry. If it's if p dot val is less than the current value and q dot val is less than current value, then we can probably keep traversing downwards. Like let's say like 6, 2, and 8 is over here. We can keep traversing downwards because we can pretty much verify that like there's gonna be no lowest common ancestors to the right. So we can do that, and then we can kind of set now what we can do is we can set the current equal dot root dot left. Yeah, that makes sense. So what this is saying is, let's say we have 628 here, and there's like it basically checks to see like if both p and q are less than the current value, then that means that lowest common ancestor has to be at some range over here, right? Well, like not for this specific case, but let's say okay, for 2 and 4, we know that both 2 and 4 are less than 6. So what we can do is pretty much we can rule out any of these elements on the right side, since we know that obviously like the root's not going to be there, so we can go towards the left. So now that we know this, we can just kind of like take a look. 2, 0, 4 is a greater now this is where we have to write down the rest of it, so we probably have to have some logic for the opposite way around. And q dot val is greater than cur dot val, then we have to have cur equals root dot right, and then yeah, and then at the very end, when none of these conditions are true, we know that, okay, let's think. So for this one, we rule out all the ones on the right. We head over to 2. We check to see like, okay, are both values greater than the current value? No, both values less than the current value. So that must be the root of the tree, because by definition of a binary search tree, anything less than has to be to the left, anything greater than has to be to the right. So therefore, if both are like not equal to each other, that means that it has to be an ancestor, because it kind of like pushes to the left or the right of that one. And in this case, it's the same value because it's 2, but it still overrules it because these two criteria hold. It's both values are either less than or both values are like a greater than. So at that point, we can then return the we can basically break the loop over here, pretty sure. Or actually, we can just return. Actually, yeah, we just return current. Yeah, so yeah, that makes sense. I'll go ahead and run it just to have a little check. It might error out. Okay, oh, typo. Of course. That's a lesson I should always double check before running again. Oh, okay. Okay, so it makes sense. Okay, great. Yeah, and time complexity of this one would be O of n because you're traversing through, and space complexity would also be O of n because for every iteration. Actually, let me think about that. Okay, because this isn't a recursive method of doing so, I was going to say that like it would be an O of n space complexity as well, because you're adding pretty much every single node to a certain a certain area. Like for example, if we're doing recursively, we'd be adding it to the call stack. But because we're not actually storing any values here and we're just traversing through, checking conditionals for each one, the space complexity of this one would be O of n. So let me just go ahead and submit this to be completely sure that it's correct. Uh-oh, it's running a little slow. You know what? There's probably an issue with this. Oh, right. Forgot to check. Maybe instead of while true, we can do while current is a possible value, and then we'll just break this, and then we'll return cur at the ends. Yeah, I think that might have been why, because yeah, like it's I guess definitely not good coding practice in order to have like a while true loop over there. Oh, that might not be the issue actually. Let's have a look. Huh. Okay, so time limits exceeded. Let's take a look over here. Okay. So you're given this binary tree. And then 3 and 5. Okay. Oh, actually, I think this needs to be an if statement because both of these need to not be true in order for that to occur. That wouldn't make sense either, actually, because that wouldn't be causing the while to be true. Oh! Oh my god, okay. There we go. That should be the reason why, because we need to actually be traversing the current one. Oh, okay, there we go. Yeah. Oh, okay. Well, let this be a lesson to me to always make sure to double check my code before completing this problem. But yeah, thank you for watching, and yeah, it's today's problem.